In this section, we want to illustrate the chain rule by the following exercise. Consider the function f(x), the composite function, given by some function g of two arguments evaluated at sine of x and x squared. And for the moment, we don't know the formula for g. If we want to express the first and second derivative of f, we only need to assume that g has the first and the second derivatives. G having the first and the second derivatives can be written g is an element of C2 in some set M, where M is some subset of R2. C comes from continuous, that means C is a set of continuous functions, not to be confused with the set of complex numbers. We don't mean complex numbers. Here C is the set of continuous functions, and C1 would be a set of functions that are continuous and have the first derivative continuous, and C2 is the set of all functions that are continuous and have the first and second continuous derivatives. So under this assumption, we can express g in terms of the derivatives of f in terms of derivative of g. We also denote the arguments of g, say a and b, so that we can use the expression for derivative of g with respect to the first argument and derivative of g with respect to the second argument. If it were just that g has just one single argument, then g prime would be a perfect symbol for the first derivative. But as it has two arguments, we need ga and gb. So we denote ga, the partial derivative of g with respect to the first argument, and we denote gb, the partial derivative of g with respect to the second argument. And then we can write the derivative f prime, or if you like, df dx. And this is the derivative of g with respect to the first argument times a with respect to x plus gb dx. And here again, ax is the derivative of a with respect to x, and a is sine of x, and it has just one argument, so a prime will be a good symbol as well. But written this way, it looks nice. Well, and if we don't have the formula for g, then we cannot simplify ga and gb. We just have to leave it this way. But as we have a being sine of x, then the derivative is cosine. And as we have that b is x squared, then the derivative is 2x. So we can do this, and we can simplify the derivative to ga times cosine of x plus gb times 2x. And now, having the first derivative, we can differentiate this once again to get the second derivative. So, derivative of sum is sum of derivatives. Okay. The first term is a product. Derivative of product, well, we know how to differentiate the product. uv derivative is u derivative v plus uv derivative, and we will need this. So we differentiate ga. But as g was function of two variables a, b, so is ga. Ga is again a function of a and b, and each of them being a function of x. So to differentiate ga, we need the same chain rule as we used a few seconds ago to differentiate g alone. So the derivative of GA is GA with respect to A once again times AX plus GA with respect to B times BX. Right? This is exactly the same chain rule as we used in this moment. Just here we apply the chain rule to G, and now we apply the very same rule to GA, the first derivative. Okay, so we are here. We are here. Times V, that means times cosine, plus U, which is GA, times the derivative of cosine, which is minus sine. Now we are here. And the second term is again a product. Here we have how to differentiate the product. So we have GB, and we want to differentiate GB. So we use the very same rule as we used to differentiate G, but this time our input is GB, the first derivative. So we take GB and differentiate with respect to A. So we have GBA times AX plus GBB times BX. You see, and this is just this rule applied to GB. So this is U derivative times B plus, we copy the first and we multiply by the derivative of 2x, which is 2, and we are done. As we have no formula for G, then we have to leave it this way, GAA and so on. But as we have formulas for A and B, we know what is AX and BX, so we can replace AX with cosine x, and we can replace BX with 2x. So we can simplify this a little to arrive at GAA times cosine of x plus GAB times 2x times cosine of x minus GA times sine of x plus GBA times cosine of x plus GBB times 2x times 2x once again plus 2GB. So this is the result for the second derivative. Well, and we could compute the third derivative and so on. So this is a very useful knowledge how to operate with these derivatives symbolically without having the explicit formula for G. This is often done in physics and physical chemistry because the functions A and B and G may describe some relation between physical quantities that are not exactly known, or we have some models, some idea of the shape of the function, but the function may change as new experimental results appear and so on.